Okay, today I'd like to look at the curvature of a parabolic trajectory. So basically, as your projectile is moving through the air, I want to know what is the curvature of the arc that it's tracing out. Notice it's not like a circle, which has a constant curvature that's fixed. It's going to start relatively flat, and then as it nears its apex or its vertex, it'll have a tighter curvature circle, and then as it moves down, it'll flatten back out. So I want to know this in two different ways. I want to calculate the curvature as a function of time as it flies through the air. And I also want to calculate the curvature as a function of x, of distance along the horizontal direction. We will need a couple facts from calculus. So we can define the curvature of a plane curve in a couple different ways. Parametrically, I can write the curvature in terms of the time derivatives of the x and y coordinates. Notice that x dot is the single time derivative dx dt. Y double dot is the second time derivative of the y coordinate with respect to t, and then a sort of antisymmetric version of that. So the dots there stand for time derivatives, or I could rewrite it in terms of space derivatives. Prime means d dx, so y double prime is the second derivative of y with respect to position x, and then y prime in the denominator is the first derivative of y with respect to position. It should be noted that these are both perfectly valid. This one will naturally be more useful if I'm writing things in terms of time. This one will be naturally more useful when I'm writing things in terms of space. Notice that both of these do depend on the second derivative in the numerator, either second time derivatives or second space derivatives. It's not equal to the second derivative. I think a lot of elementary calculus students think that curvature is the second derivative when you're doing sort of a concavity type argument. Well, they're related. They have the same sign, SIGN, but there is this extra denominator that accounts for the fact that the slope's directions will be changing as well as the actual second derivative. Okay, so let's jump right into it. I'm going to go ahead and calculate kappa of t first. So this is not a k, it's a kappa. Try to make it as kappa e as possible. And I'll be just using this first equation because it's very much in terms of time. X dot stands for Vx. Now, I went ahead and rewrote some stuff from kinematics that we already know about these parabolas. The x velocity component is a fixed constant. That's the whole interesting thing about parabolas. It only accelerates vertically. So that is just going to be V naught cosine theta. And notice that x dot is indeed Vx. It is the x component of the velocity. The second derivative of y will be the acceleration in the y direction. Or if you want, take a time derivative of the y velocity. Either way, you'll get negative g. It's a constant. That's the whole idea behind the acceleration under the influence of gravity. The second term will involve v naught or vy, which has two terms to it now. But notice that x double dot is the acceleration in the x direction, and that's 0. So that term will just kind of go away. That's nice. The denominator is a little messier, but it's not so bad. So x dot squared will just be v naught cosine theta, quantity squared, and y dot squared will be the other one, squared. All of that is to the 3/2 power. So now let's see if we can simplify things a little bit. Notice that in the numerator, of course, that's a 0. I'll pull out this negative sign because the curvature is actually negative for all of these parabolas. They are concave down, so I am expecting negative curvatures here. The numerator will just be g v naught cosine theta. There's really no simplification we can do there. The denominator does have a little bit of simplification. When I square this and then I square this binomial out, this first term squared, v naught sine squared, and this v naught cosine squared can be added together as a Pythagorean relation as v naught squared. So those combine nicely. Unfortunately, the rest of it does not. We just have to leave it like that. So we'll have a 2 v naught g t sine theta, and then plus g squared t squared, all to the 3/2 power. So notice the curvature does depend on time. We weren't really surprised by that. It starts off with relatively low curvature. In fact, you can go see what is the curvature at launch That's when t equals 0 here. So maybe I'll write that over here. K naught, the initial curvature, or kappa naught, is when t equals 0. Notice I'll have a v naught squared to the 3/2. That's a v naught cubed in the denominator. So I'll have minus g cosine theta over v naught squared. So that is my initial curvature for this projectile. Okay, let's clear this off. And now I'm going to try to find the curvature as a function of position using the second relation. Okay, so now what we want is to use the trajectory equation. I am again choosing an origin where it launches from the origin at angle theta. So we've used this before. I need to find the second x derivative of this. Well, notice the first term is linear, so 2 derivatives will kill it off entirely. The second term, pulling down a 2 from the first derivative and then taking another derivative will get rid of the x. It will also be a constant. It'll be a negative constant, and it'll be g secant squared theta over v naught squared. Notice the 2 canceled when I did the first derivative. The denominator, put some brackets here. Y prime is just a first derivative, so that'll be tan theta minus gx over v naught squared secant squared theta squared, all to the 3/2 power. Now we could go ahead and square this out. Doing so might be kind of convenient because tan squared, especially +1, can be written in terms of secant squared. So let's just go ahead and do that. So I have a minus g secant squared theta over v naught squared. In the denominator, we'll have this big ugly beast, but indeed 1 plus tan squared is secant squared. I have a secant squared here. I have a secant to the 4th here, so I can factor out a secant squared from everything. Notice that it's to the 3/2 power, so it becomes a secant cubed, which partially cancels the secant squared here in the numerator. Let me do all that simplification and move it up. Okay, so here it is. No more real simplification that can go through, unfortunately, but that is our kappa of x. One thing we might want to add as well, what is the curvature at the peak of our projectile? We've already seen that the initial curvature is given by this relation. I want to know what is the curvature at the highest point. Well, we can use actually either of the curvature formulas we've derived. Let's go ahead and use the one that's already on the board. Notice that at the peak, my x-coordinate is half the range. And if you use the range formula, you'll end up with this expression after dividing by 2. Now all that remains is to plug this back in for x here and here, clean things up. There will be a lot of simplification. For example, the x here, v naught squared over g, will cancel there. The x squared, v naught to the 4th over g squared will also cancel. So I really only will have trigonometric relations here. I'm not going to go through all the details right now. It does actually simplify quite a bit. So I'll write this as kappa m or something. So this is the curvature at the maximum point, in other words, the vertex. That will be g secant squared over v naught squared when all is said and done. Notice it's got a similar form to the launch curvature, but it has a secant squared theta instead of a cosine theta. Okay, I want to do one last thing with this information that we've just found, and let me put that up on the board right now. Okay, let's use this information about the curvature to solve another problem from physics. Let's imagine you're standing on the peak of a circular or spherical hill. So this is an arc of a circle. And you want to kick a soccer ball or something horizontally, just straight horizontally, with the minimum speed so that it does not re-intersect with the hill that you're on. So no bouncing down the hill several times. I want to know what's the minimum launch speed horizontally so that my parabola does not intersect this circle. Well, the utility of curvature is that it tells us, or can be computed into a radius. What is the radius of the circle that best fits a particular curve at a particular point? And in fact, it's just the reciprocal of the curvature, or the absolute value of the curvature. In other words, if we want this to be true, I want to make sure that the radius of my circle, the arc that I'm trying to avoid, is less than, or maybe equal to, 1 over the curvature at the launch point. Now, I could either use the curvature at the launch point or the curvature at the maximum formula. They're the same in this case because I'm launching it from its maximum. Notice that theta equals 0 here, so secant squared of 0 or cosine of 0 will give me the same result. I do want the absolute values here because, of course, the curvature is negative, but I'm looking at a radius of curvature, and that really should be a positive value. And when we plug that in at theta equals 0, which is this horizontal condition here, I'm going to end up with 1 over, absolute value gets rid of the negative sign, g over v naught squared, secant squared or cosine both give me 1 for a horizontal launch. Shuffling things around, that tells me that I want my launch speed to be greater than or equal to gr. Pretty nice. That equality there would be the minimum speed so that it just barely misses reconnecting with this circle. So notice we have that the circle and my launch point do have the same launch height and they're tangent to each other, but that's not quite enough information to make sure that they don't re-intersect each other. I also need the radius of curvature of my parabola to be larger than the radius of curvature of my circle. Now, the circle has a fixed radius of curvature. That's why this works. If this was like an ellipse or something, we wouldn't really know necessarily. But because it's got a fixed curvature, I just need to make sure that the radius of curvature starts larger than that, and then I'll be guaranteed that it will remain smaller. Last thing you might want to do if you're interested, find out where this landing point is. I'll let you do that as an exercise, for example. I'll just tell you that it ends up being the square root of 2 times this radius. So it's an extra 40% further out than the bottom of your hill. QED.